Hello! This video is for Module 1, Part 3, and includes a discussion of multiple linear regression as a predictive analytics tool. Okay, let's go ahead and get started. So multiple linear regression is an extension of simple linear regression, and the extension is that more than one predictor variable now is going to be used to understand the response variable. Here, the main goal of performing a multiple linear regression analysis is to obtain the best possible predictions. All right, let's look at example 1.3. We are again going to use data from the Centers for Medicare and Medicaid Services regarding the complications and deaths from nearly 4,850 different hospitals across the United States. Some of the relevant fields include the facility name, the state in which the facility resides. We're going to be investigating the PSI 90 score, which again is the CMS Patient Safety and Adverse Events Composite Measure. A lower value for this measure is better. The predictor variables that we are going to consider here are PSI 03, which is the pressure ulcer rate or bed sores rate. We have PSI 09, which is the perioperative hemorrhage rate. Probably saying that wrong. And then PSI 13, which is the postoperative sepsis rate. For all of these variables, a lower value is better. We are going to narrow our focus and only include states that are in the upper Midwest. So North Dakota, South Dakota, Minnesota, Wisconsin, and Iowa. Once again here, the files folder will contain the data and also the module or collab document for module 1.3. So all of the graphs and output can be obtained from that collab document. Okay, let's look at some initial scatter plots then. So again, my response variable that I am trying to make predictions for is the PSI 90. So that is going to be on the y-axis in each of these plots. And on the x-axis, I have the three different predictor variables that are being considered here. Now, in a multiple linear regression analysis, we are considering the collective effect of these predictor variables. Here, when I'm looking at just these individual scatter plots, I'm looking at their individual effect. But this gives us a view at what the potential effect of each predictor is against my response. So here, the plot on the left is for PSI 90 versus PSI 03. And we can see that the trend in this plot is the strongest. The correlation measure in this plot is about 0.8. Again, the correlation measures go from -1 to 1, and the closer they are to 1, the stronger the positive relationship will be. So we can see that PSI 03 has a strong, certainly looks linear relationship with PSI 90. PSI 13, which is the sepsis rate, also has a somewhat, maybe a mediocre or a fairly decent relationship with PSI 90. The correlation measure here in this plot is about 0.42. So certainly not as strong as PSI 03. PSI 09, okay, which is our hemorrhage rate, that has a weak correlation here with PSI 90, with a correlation measure here in this plot of only about 0.2149. Some of these values in these plots are extreme, so this point here would be extreme, or maybe this point over here. This one looks quite high relative to the others. Points that are extreme in the predictor variable direction So along the y-axis, x-axis here. So like this point here would be an extreme along the x-axis. Those are called high leverage points. Points that are extreme in the y direction, like this one here, would be considered an outlier. So we do differentiate the types of points if they are an outlier or extreme in the predictor variable direction versus being an outlier or extreme in the response direction. The effect of high leverage points and outliers should be carefully considered when you're doing a multiple linear regression analysis. When the goal is simply to obtain the best predictions possible, we certainly want to consider those extreme observations, but those are of less concern than if we were trying to investigate the relationship or the effect of each of these predictors on the response. Okay, how do I get the multiple linear regression output then? Well, we're going to use various computing technologies will allow us to do this. Here I have syntax for using R. And again, the Colab document is where you would use R. The only thing that's really changed from simple linear regression is that I've just changed my formula. So here I have my first predictor plus my second predictor variable plus my third predictor variable here. So this portion of the command is what actually gets changed there for the different types of models that I'm going to be fitting. Here's our output from that multiple linear regression analysis. Again, the output that I want to concentrate on here has been highlighted. This output looks very much like it did before, with the exception that I have more than two estimates now. I'm going to have a y-intercept. I'm going to have a slope for the PSI 03 direction. I'll have a slope for the PSI 09 direction, and also a slope for the PS 13 direction. Writing out the prediction formula, we will just use these estimates. So I have predicted PSI 90, that's the response that I'm trying to make predictions for, are going to be the y-intercept plus the coefficient on PSI 03, which is 0.293. I'm going to have a coefficient again for PSI 09, which is 0.057. And then finally, I'll have the coefficient for PS 13, which is going to be 0.73. When we're looking at the interpretation of the slope of these quantities, it is similar to what we did with simple linear regression with one exception. So if I'm investigating the 0.293, okay, what we would say is that if the PSI 03 value or rate is increased by 1 unit, this is going to be how much the predicted PSI is expected to increase. This is a positive here, so it's going to increase. Now there's one additional condition or thing that I should be worried about when I'm interpreting this 0.293. And that is, I cannot change the PSI 09, nor can I change the PSI 13 here. So when I'm trying to understand the effect of this predictor variable, these others cannot change at the same time. So what we often say is that these other predictors, if they were to remain constant or not change, then a 1 unit increase in PSI 03 will increase my predicted PSI by 0.293. So let's try to interpret the PSI 13 then for a minute. What is this 0.073 telling me? So if I hold the other predictor variables constant, so holding PSI 03 and 09 constant, if I increase PSI 13 by 1 unit, I can expect the PSI 90 to go up by 0.073. Again, the interpretation of the y-intercept is usually not meaningful and will be skipped here. To make predictions, all I need to do is to enter in the values for PSI 03, 09, and 13. So here I have a hospital that is in Marshalltown, Unity Point Health here. Suppose that the predictor variable outcomes for this hospital are, for PSI03, it's 0.44, PSI09, it's 2.51, and PSI13, it's 4.74. I simply need to just enter these values into that equation, into my prediction equation. So I would take the PSI03 value for this hospital, which is 0.44, and I would need to multiply that by the coefficient for PSI03. I would take 0.057, which is the coefficient for PSI09, and multiply by the PSI09 value for that hospital, which is 2.51 here. Likewise for PSI13. Once I enter these predictor variable values into my prediction equation, I can obtain a prediction. So for this particular hospital, I would get a predicted PSI90 value of about 0.93. The prediction error is simply computed by taking the actual minus the predicted. The actual value for this hospital is 0.92. The predicted value for this hospital is 0.9296. So my prediction error is pretty close to zero here. It's pretty small. It's a little bit negative. So my predicted value is just a little bit too high. Okay, the next thing then is to understand the importance of each predictor variable. So I have 3 different predictor variables that went into this prediction equation. And we oftentimes want to know which of those predictor variables are more important than others. So certainly some predictor variables are more important than others in a prediction equation. Also, there are many different combinations of the predictor variables that may be considered when building a regression model. Okay, so we don't necessarily just automatically dump all 3 predictor variables into our prediction equation. There's oftentimes more consideration that goes into play there. So what I've done here is looked at the 3 simple linear regression models, the one that has PSI03 in it, another model that has PSI09 in it, and another model that has PS13 in it. So the question we might initially ask is, which of these predictor variables is most relevant to PSI90 when I'm just using a simple linear regression model? Now, clearly we can see that the R squared for model number 1 is considerably better than the R squared for model 2 or 3. The root mean square error, which we want that to be small, is considerably less when I'm looking at model number 1. So what that means, or what that tells me, is that PSI03 is an important, helps me understand PSI90. It is an important predictor variable. PS09 is not helping me understand the response variable very well at all. So PSI03 appears to be the most important when I'm looking at them individually. Let's look at the next set here when I'm looking at 2 predictor variables. So I have 03 and 9, I have 03 and 13, and then 9 and 13. And out of these 3 models, which appears to be doing the best is the one that has PS03 and 13 in it. Again, the root mean square error is smallest here. My R squared went from 74.6% when I just had PSI03 in it. It jumped up to 86.1% here when I added PSI13. So in that sense, PSI13 must be the second most important predictor variable. The last model is when I put all 3 of those in. So here, going from model 5 to model 7, what I've done is just included PSI09. My R squared went from 86.1 up to 87.5. So there was an increase there, but not much of an increase. Likewise, in the root mean square error, there was a decrease, but not much of a decrease. So PSI09, okay, adds a little bit to my understanding of the response variable, but not a whole lot. And what that means from a practical standpoint is that PS09 is not contributing much to our understanding of the response variable. Thus, whether or not I include or exclude that predictor variable is likely not to adversely affect my ability to make accurate predictions. It certainly adds to my accuracy a little bit, but not a lot, because my R-squared didn't jump up much, or my root mean square error didn't drop much when I went from Model 5 to Model 7. Some may advocate that you use Model 5 to make predictions. It's a little bit simpler, and it's doing nearly as well as when I'm adding PSI09 as a predictor variable into my model. I'm going to go ahead and just use model number 7, okay, because it does add a little bit. And again, I'm not too worried about how complicated the model is. My goal here is just to obtain the best possible predictions, and model 7 is going to do that. Okay, let's consider the variable importance plot. So a variable importance plot is a little bit easier than having to go through and consider all the possible models that I might have. And what we do with a variable importance plot is just look at the importance of each of the predictors. Now, how we go about doing that depends on which machine learning algorithm that we're using or predictive analytics method that we're using. When I'm doing multiple linear regression, what I do to understand the importance of a predictor variable is to consider the t-value in the regression output. The t-value is simply computed by taking the estimate divided by the standard error. So if I take 0.29 divided by 0.01, that's where this 28.46 is coming from. We're going to do that for each of the predictors. The larger the t-value is, the more important the predictor is. Now, if my estimate is negative, my t-value will actually be negative. So what I mean by large here is large in magnitude or large in absolute value. Any t-value that is bigger than 2 is going to be considered large, or that predictor will be important. Some people will use 1.5 instead of 2 to identify important predictor variables. Now, these t-values are often just plotted on a bar graph like this here. So PSI03 has an absolute t-value of 28. 13 has an absolute t-value of 12.44, and PSI09 has an absolute value of about 4.4. This red line here is just at 2. Again, that red line could be at 1.5 if you wanted as well. Any predictor whose bar exceeds this value of 2 would be important. So according to the variable importance plot for this analysis here, PSI09 is indeed important in helping me understand the response variable. So even though it increased the R-squared just a little bit, okay, the variable importance plot suggests that that variable should be included. If you have one of these bars that sit below this red line, then that's going to suggest that that variable, predictor variable, is not that important to understanding the response. Again, if the goal is simply to get the best possible predictions, you could leave those variables in the model. It's not going to hurt you to have them in the model. Those variables are just not necessary in helping me understand what's going on. Next, let's look at the predicted versus actual plot. The interpretation here is the same as what we had for simple linear regression. My R-squared is at 87.5% here. Okay, so from my model, where's my model output? Way up here. My R-squared is at 87.5. And that's pretty good. Remember, the R-squared ranges from 0 to 1. So having an R-squared of 87, almost 88% is pretty good. Looking at this plot, you can see that the points closely follow our y equal x line. Again, the y equal x line is where the predicted values match the actual values. And for the most part, these dots follow pretty closely on that line. So we have a pretty good model here. We're going to be able to make accurate predictions with this model. We can also look at the root mean square error. I've mentioned that up above. The root mean square error from the model that has all three predictors in it is about 0.057 or so. We can compute the mean absolute prediction error. Again, the mean absolute prediction error is simply going to be these prediction errors here. We take the absolute value of those, and then we just average them. That's the mean absolute prediction error. I'm going to have just one number, okay, which would be the average of all of these after you take the absolute value of those. And again, that gives you just kind of a general idea of how much error I can expect in my predictions. The MAPE value here is 0.042. These values, okay, are pretty small considering the fact that the PSI 90 values range from about 0.75 up to 2.0. So being off by 0.05 on average is indeed pretty good. Another way of looking at those averages is the distance from these points to the green line here is about 0.05. So again, that's just measuring how tight these points tend to be against this green line. Some other things that I've done here is just to compute the MAPE for each of the states individually. This just allows me to look at the quality of the predictions for each state separately. So this value up here, the 0.042, was the average or the mean absolute prediction error for all of the states together. And here what I've done is computed those for each state separately. You can see that for Wisconsin, the predictions have a MAPE value of about 0.037. And for, looks like North Dakota is the highest at about 0.052. So a little bit worse here on North Dakota and South Dakota. Predictions seem to be doing the best for the hospitals in Wisconsin. Another thing that I could do is to look at my prediction error scatter plot, but just color code the points by the different states. And what I'm hoping for in this plot is that the different states are just kind of intermixed here. And they do look indeed intermixed. It would be really bad, for example, if all of the Iowa points were up high here, because that would mean that the predictions were off for all of the Iowa points. We would say that there would be bias in those predictions. But that's not the case here. The colors, again, seem to be pretty dispersed vertically in this plot, which suggests that the predictions are equally good, okay, for the most part across the states. I don't have any biases in these predictions for one state over the other. I can rank, again, the prediction errors. So positive values would be bad here. For this particular hospital, their actual PSI 90 score was about 1.2. Given their information about PSI 03, 09, and 13, I would expect their PSI 90 to be about 0.95. Their actual was 1.2. So again, they're much higher than what they should be given information about these three predictor variables. Another one that's doing poorly is St. Luke's Regional Hospital here. Now, there might be reasons for why these values are higher than they're predicted. Okay, but when I'm looking at the PSI 03, 09, and 13 predictors, their predictions are much lower than what their actual values are. On the other hand, the large negatives, Mercy Hospital in Coon Rapids here, okay, their actual PSI 90 score was 0.88, and I predicted it to be 0.99. Okay, so again, they are well under what I predicted it to be. Another here is St. Cloud Hospital. I think we saw that on our list earlier in the simple linear regression module. Their actual was 0.73, predicted to be about 0.85. Again, they're under what they should be. So what we really want to worry about, or at least from a modeling perspective, is not so much what these values are, but how much lower or larger these values are from what I expect. Okay, for the task here, I have gathered hospitals in California and fit a multiple linear regression model and gave you the variable importance plot. And I also gathered data from North Carolina, gave you the regression output and also the variable importance plot. I have a set of questions here for you to answer, including some true-false questions, a couple scatter plots down here from the prediction errors. Go ahead and submit that information or try to answer that information and hit submit, and then of course my answers will be given to you so that you can check your understanding. Okay, that does it for this module. Thank you and have a good day.